So good morning. Today we are going to look at an important topic called anti-lock brake system. So the name itself suggests the main function of your ABS anti-lock brake system is to prevent rolling wheels. Locking is what is its basic function. So it's prevent tires from locking, and it can ensure because of that sufficient it is going to ensure that steering control of the driver would be ensured. So that is going to help a vehicle to generate the necessary force to resist the side force, some disturbances, or to ensure the stability of your vehicle. Right, that's what is the role of ABS, and we're going to look at that in detail, its functioning aspects, and all in this particular lecture. So let me share my screen for today's class. So hope the screen is visible. This is lecture number 41, and today's date is 3/12/2021. We're going to study about ABS called anti-lock brake systems. Anti-lock brake system. So this is also otherwise called the electronic stability program. By Bosch, which is proudly say invented for life. So if you look at Bosch company has got a monopoly, the full hold of this ABS system. So if you look at this ABS in vehicular application, we see a very important aspect of any vehicle is its safety system. So the safety system can be a passive safety system. Passive safety system or active. Active safety system. So if it is passive safety system, the example in your vehicle are your seat belt or your airbag, crumble zone. So these are all something which is not going to prevent accident. Accident would have happened, but this safety system would ensure the life of the driver and occupant. So that is what is called the passive safety system. That is not in a control of preventing accidents. Whereas active safety system, if you look at in a vehicle like ABS, is an active safety system. Today, whatever we are going to see is an active safety system which can prevent an accident occurring on event only. Right. So one such system is what is this ABS. We also have another ABS system like night light vision, and emergency braking, that is automatic braking, and your total control of your vehicle in lane changing and so on. There are many active safety systems that are there, adaptive cruise control. So these are all some of them to mention what are active safety systems. So this ABS is one such system, is what today we are going to look at it. Right. So we have to understand now some of the important terms. So what are those? So like in acceleration, we have understood what is called the slip that is occurring at the tire road interaction, right? We know what we mean by longitudinal slip. So how do we define longitudinal slip? By letter I, and that would be defined as R omega minus V by R omega into 100. So this is what we have seen. So where r is rolling radius, omega is angular velocity of your wheel, and where this v is its wheel center linear velocity. So the question is that not same? R omega is not equal to v. It is not. Why is it? Because longitudinal slip is defined when during acceleration. So during acceleration, if I define this, you see that the tire is a pneumatic tire, and the tire carcass is going to get compressed during driving torque is applied on the driving wheel. At that time, if you look at the radius is not free rolling radius. So this V would be equal to effective radius times omega. This effective radius would be smaller than that of free rolling radius. That's happening is because of there is a compression of your tread. What I mean by that, there is a compression of your tread during driving torque applied. If I stretch my tread of the tire, it is going to be what 2 pi r. But the compression would make the length of the tread would be smaller than 2 pi r. Right? That is what is happening. So that would result in the equivalent translation of your wheel center would be smaller than that of what would have happened during free rolling condition. So this r omega during free rolling condition, whereas v is during acceleration. If that is so, the distance, equivalent distance would not be same as that of 2 pi r for one revolution of the wheel, and that is why you are able to define the slip. So for the given r omega, what is this difference is what is defining your slip. This is during acceleration. So on the other hand, during braking, so what is happening? Your braking torque is applied by the brake system of your vehicle on the wheels. And at that time, the tread, instead of getting compression like case of an acceleration, getting stretched. The length of the tread, if you are unstretched, if you are cutting and stretching it, that length 2 pi r would be greater than that of the one which is originally there during free rolling condition. So at that time, the scenario of V is going to be greater than R omega. In this case, R omega is greater than V. So that's what you should understand. So the wheel center velocity is greater than R omega during braking, and that is where you define a term called the skid. Skid, like slip, you have another phenomena that is necessary to happen for braking action is skid, and that is defined by IS, and you define that as V minus R omega, which is greater out of these two should come here. This difference for the given V into 100. So this is how you define skid. So if you have this skid now understood, if you look at the requirement of your braking characteristics for the function of skid can be defined now. What are that? Let me look at here. Instead of putting braking effort, I will put braking coefficient. That's called a braking force coefficient. CB. That's called braking force coefficient. So how do you define the CB? That's nothing but actually your MEE only. Our MEE would vary during the scenario. That's why this coefficient CB is defined as what is the braking force divided by the normal load. This is what is defining CB, that is braking force coefficient. So that if you look at, that would vary if I take IS skid on my horizontal axis 0 to 100% if I take. So how does it going to vary is, say this is now 20%, 40%, 60%, 80%, 100%. So you would see that the skid would vary something, sometime linear, and then your CB would vary like that, and suddenly it will fall to this, where this is corresponding to your mu s times W, whereas this peak would be corresponding to if this is it's not mu s W, it is only mu s. And this is what is now your CB, and that value would be MEP, you can say. So this is how it varies. It is normalized by the normal load. So this is the coefficient. On the other hand, if you look at another coefficient also, that is for your cornering force that is developed, that would be cornering force coefficient. So why do I have to look at cornering force coefficient also? Is because you are not going to have this braking action not only on a straight line motion, also when you have to take a hard corner, particularly the road visibility is not there and you have to take a corner, you see some unexpected environment. As you look at after during the cornering, there are scenarios, tough scenarios of driving and cornering. At that time, this cornering coefficient, if you look at, it would be having a maximum value when skid is not there. As the skid happens, that coefficient value would be reaching this, and it may reach to null value. There is no coefficient at all. So the coefficient is not constant, that value would be varying. So what does that you understand? If I have my braking action, my skid is limited by this operating range. In this operating range, I would be able to have my braking force developed at the tire road interaction maximum. If it reaches beyond the skid value, some 20%, so it may be maximum of 20% corresponding to this is 20. And then what will happen? All of a sudden, this coefficient value would drastically drop down to a static coefficient of friction, where this is going to be 100% skid. What do you mean by 100% skid? A wheel locked and then tire skidding. There is tire road contact would be sliding instead of rolling action takes place. There is no slipping that's possible at all, right? So it is very, very interesting that when I drive my vehicle, I'm accelerating, wheels are having slip phenomena. So there would be forward force, it's an acceleration. When I apply the braking action, that is decelerating. So when braking force comes, the tractive force disappears on the drive axle. On a non-drive axle, if you look at, there is only braking force appearing. Of course, there is no tractive effort appearing on the non-driving wheels. So these are all something it's important to understand. So for the sake of today's class, let us look at closely the free body diagram of your tire rod interaction during braking, the tire dynamics during braking. So let me just consider my tire wheel is represented by the circle. Now I draw, and this is center of the circle, and the center of the circle goes in this direction. See, this is this V velocity, forward velocity. So you know that during braking, so braking, what is that? The brake torque is applied by the brake system. We'll look at immediately now after this, what is brake system, this ABS circuit and so on. So when I had to apply brake torque, this is the rotational direction before application. So this is my angular velocity and my brake torque would be applied opposite to that. So that is TB. That is my braking torque. The moment the braking torque is applied here, I would have my braking force against the translational direction, that is FB. And this braking force is function of mu P times Fz. So what is Fz? Is normal. So here I have Fz, which is normal, and that's because of the load that is acting on the wheel. So this is its free body diagram. It's not only there. And what is additionally there here is the kinematic parameter. If you look at this omega now, because of this, would start decreasing. If this start decreasing, what does that means? Your omega dot would be happening. So omega dot would be deceleration in the opposite direction. Omega dot, right? And you would see that this FB would facilitate here a moment at the wheel center. And that moment we call it as a tire torque in the tire, and that would be FB into R, radius of this wheel. So FBR. So now if I take my free body diagram and I take moment about the center of the wheel, I would have this equation. What is that equation I'll have? I would have this following equation. So I will, this is that I will get. So look at when I take moment about this center point, I will have a counterclockwise moment positive, then this torque Tt minus Tb is what is going to be. If this is my angular acceleration, there will be inertia torque, that is I times omega dot in this direction, and that's what is equal to here, I times omega dot. So I can get now omega dot would be Td minus Tb by I subscript W, that is wheel rotational inertia. So this Td is nothing but this Fb braking force into R minus Tb is the applied torque by I omega is what is going to be equal to angular deceleration. So this is that simple equation that I get it out of this free body diagram. And it is clear that there is also an associated deceleration, linear deceleration at this wheel center, and that is AC, and that is not going to be equal to R times omega dot. That's why you have this skid phenomena and so on, right? So now I can have the difference. This omega dot can be positive or negative. If this omega dot is positive, what does that mean? It is decelerating. If this is negative, it is still under acceleration. That's what you have to understand, right? Okay. So now with this free body diagram and what is happening at the tire wheel interaction, let me just go into explaining what is this ABS system in our vehicle. Right, so let me just clarify this point once again. When the difference in this FBR minus TB is positive, right? If FB into R minus TB is positive, what does that it refers here is the tire accelerate. Take this statement, tire accelerate. If FBR minus TB is negative, then tire decelerates, right? So that is, so when it is negative, what does that means? You have TB applied torque is more, it's limited by FB developed at the tire road direction. So this has become negative. At that time, whatever your omega dot that you have would be deceleration. That's what it is in clockwise sense here, in this direction. If this is happened to be positive, that means you would have this changed, then omega dot in this direction corresponds to acceleration. Because this would be flipping. In ABS, you don't have your brake action is only to decelerate your wheel. Your wheel would be within a millisecond duration, accelerate, decelerate. So it will be reducing the speed, and then again it will stop reducing the speed. That time it will be increasing the speed, wheel speed, then again decreasing. So it is gradually going to take your vehicle omega of this wheel to 0. So that's what you are going to witness now, and how that is working. So if you look at this ABS in your vehicle, it is the electronic feedback control system. So when I say that, I would have my circuit goes like this. I will have, if this is my wheel, and I would have here in this wheel a pickup sensor, pickup electromagnetic sensor, and that sensor would be somewhere here, and there would be a toothed wheel attached with this rolling one. So this pickup would send signal some 90 to 100 times per revolution, and it would pick the speed of your wheel, and this would be sent to control unit, correct? So this speed would be sent to a control unit called electronic control unit. right? On the other hand, if you look at the brake system would have necessarily starting from my brake pedal. So there is a brake pedal here. This is brake pedal. So when I apply a brake here, this brake pedal would give a signal to a cylinder called the master cylinder. There's a master cylinder. So you'll have here a fluid, and this fluid would be sent to a cylinder here, which is wheel cylinder. This is called the wheel cylinder. To this through a modulator. So this is what is called a modulator. What is this is called hydraulic modulator. So hydraulic modulator. So you can see that as I give a pressure on my brake, and then the cylinder, master cylinder pressure fluid would flow through this, and this modulator would send the requirement of fluid to this cylinder, wheel cylinder, and this wheel cylinder would apply my TB, braking torque, right? That is how it acts. And this pressure on this would be modulated by this hydraulic means. That's why it's called a hydraulic modulator. Why this modulator required here? Why can't we connect straight away from here through the cylinder? Because if I do that, whatever the pressure mechanically given by the driver, and this pressure cannot vary. So maybe here the pressure is small and the pressure is increased at this point applied, but it has become passive system. Where this modulator is there, the modulator would accordingly create the pressure required on the wheel cylinder. So this modulator get working how? This modulator get a signal again from this ECU. So this ECU comes here. So if you look at the hydraulic modulator receives a signal from ECU. So what signal ECU would send? The ECU would look at here and it will monitor the speed. If the speed is reducing and the wheel is about to lock, it will send the signal here. And the electronic control unit would understand there's a need of act of pressure release in the cylinder, because the wheel is about to lock. But what is required is the wheel should not lock, is what is the function of your ABS. And then the modulator would act and reduce the pressure, and this will be prevented from locking. Once it is prevented from locking, again the signal will come here and it will sense that now this speed is going, but the speed is going beyond some value. It is not, because your braking action to happen. So your braking action to happen, not all of a sudden locking, it has to happen gradually. So within few millisecond duration, it has to function like release pressure, increase pressure, release pressure, increase pressure, like that. So that cycling of application of brake pressure reduction is not to zero, and again it has to increase, then again it has to decrease. That the cyclic, so it has to reduce hold and increase hold and reduce hold, like that cycle should happen, and that is how this goes. So there will be a threshold values of this, looking at your R times omega, what is that corresponding speed, or R times omega dot, R times omega dot should be having some range of value, and accordingly this would be acting. So this is how your ABS functioning. So essentially it will have what all the components it will have. First, this one called the sensor, and this sensor is pickup sensor, electromagnetic speed pickup sensor. Number two is what is this ECU. Number two is electronic control unit. The function of electronic control unit, receive the signal and see that is it saying that wheel is about to lock, then send the signal here, and the pressure is reduced, and then wheel is averted. It has to be averted. No, this locking is averted. Then again, signal will be sent to increase the pressure and so on. So that is the role of this electronic control unit. Send the signal to the hydraulic modulator. So number three is the hydraulic modulator. This is number three, hydraulic modulator. And number 4 is your wheel speed. Wheel cylinder. Wheel cylinder is number 4. Wheel cylinder. Wheel pressure cylinder it is. And then number 5 is, of course, your master cylinder. Number 5 is master cylinder. Number 5 is master cylinder. Right? So this is how it functions. And if you look at this function would happen how, looking at this, if you see, it would make all the time this is working in this desirable range. So the skid value would be taken to that optimum value, so that always it would be working here. So I would be able to tap the maximum braking force. And this diagram is drawn for a particular slip angle, at a slip angle. That's very important. So you are going to see something called a friction ellipse. All in tire dynamics we'll discuss. So if the slip angle requirement to increase whenever there is a side force increases. So I take one particular slip angle and then I look at the variation of my coefficient, braking force coefficient and cornering force coefficient like this. And if it is acting in this zone, it won't rapidly fall onto this 100% skid, and then 100% skid, the necessary lateral force is almost null, 0. So when there are necessary side force to support your vehicle is reaching to 0, that is going to take your vehicle unstable state, right? That's all something that we have discussed. So I'm going to present some videos for you to better understand the need of this ABS and working principle, what I have explained, again to listen from the video, and then let us look at importantly the characteristics of ABS and different ABS systems that are employed in a passenger car. So another 15 minutes we will complete our lecture. So let us just listen now for this video. So for that purpose, let me unshare my screen and change the screen to the next one, right? Let's go watch this video. So hope you are able to hear this audio as well now. Are you able to hear the audio?
Yes, sir.
Yeah.
Passive safety systems provide protection when the accident has already occurred. Active safety systems help to prevent accidents occurring at all. ESP, the Electronic Stability Program from Bosch, is an innovative safety system that actively supports the driver and keeps the vehicle safely on the road in critical situations. A situation that occurs frequently. You're driving on the motorway in a vehicle without ESP. In spite of the heavy traffic, the wide road means you can relax behind the wheel. There are no reports of accidents or traffic jams. Suddenly, an obstacle appears in front of you. A sudden steering maneuver to avoid a collision, the vehicle starts to skid and you lose control. The Electronic Stability Program, ESP, monitors the vehicle 25 times a second. If it detects that the car shows a tendency to swerve, the system reacts immediately. Precisely metered braking forces take effect on the individual wheels and return the vehicle to its lane. This is how ESP safely gets the driver out of a dangerous situation. The course of a road cannot always be correctly judged. For example, even a single bend can be tighter than expected. The vehicle is moving too fast. The centrifugal force pushes it outwards and it swerves out of line. ESP compares the driver's intention with the vehicle's actual behavior. If the vehicle deviates from the desired course, electronics intervene at lightning speed. Without any action on the part of the driver, the system applies braking force to individual wheels, reduces engine output torque if necessary, and stabilizes the vehicle. Current studies show that 25% of all accidents resulting in severe injuries are caused by skids. ESP counteracts the danger of skidding, keeps the vehicle safely in its lane, and thus minimizes the potential risk of accidents. ESP does not override the laws of physics, but it does provide effective support for prudent drivers in critically dangerous situations. Electronic Stability Program from Bosch, a new milestone in active driving safety.
Bosch, invented for life.
So this video has given you an importance of this active safety system in your vehicle, and which doesn't disobey the laws of physics. It is enhancing the laws of physics with an appropriate control strategies. So that's what we have looked at for different vehicle environmental scenario, whether it is the highway to suddenly to take your steering action call, or it is on a very hard cornering on a different road surface. The two different scenarios, how this electronic stability program, this ABS can protect the vehicle from meeting with an accident, going into the unstable state, is what is prevented, is what we witnessed. And let me just share another couple of videos for looking at in detail again this ABS, right? So just wait. Let's watch this video of safe braking by ABS again.
Safe braking with ABS from Bosch. The need to be mobile is rising. Traffic is growing ever heavier. Critical traffic scenarios are increasing. With unclear traffic situations, suddenly occurring traffic jams, or obstacles, sometimes only full braking can save the situation. When applying full brakes in critical situations, or when braking on slippery roadways, the wheels can lock. The vehicle can no longer react to the driver's steering because the locked wheels can no longer convey the optimum braking power and necessary turning force to the street. It hence becomes nearly impossible to evade an obstacle. ABS, the anti-lock braking system from Bosch, prevents locking of the wheels. ABS ensures that the vehicle remains steerable and stable while fully applying the brakes. The ABS control unit also continuously monitors all wheels by means of wheel speed sensors. Should the system recognize that a wheel is locked, ABS immediately intervenes and systematically regulates braking pressure. ABS can regulate each individual wheel within milliseconds. With the electronic anti-lock braking system, a sort of electronic intermittent braking, ABS achieves stability and steerability with the shortest possible braking distance. Let's have a look at the ABS benefits in practice. Full braking at 100 kilometers per hour. With ABS, the braking distance is significantly shorter and the vehicle remains stable. full braking in a curve. Without ABS, should the wheels lock while applying full brakes along a curve, the vehicle can no longer be steered and slips out of the curve. With ABS, you have the vehicle under control and you can steer systematically. Full braking and swerving. Should the braking distance not suffice, the driver must swerve to evade the obstacle. Without ABS, the vehicle cannot respond to the driver's steering attempts. With ABS, your vehicle remains steerable and stable. A collision is thus avoidable. Full braking on different surfaces. Traction on lanes may vary due to volatile weather, dirt, and foliage. When fully applying brakes without ABS, the vehicle can quickly become unstable. With ABS, the vehicle remains stable, even in this situation, with an optimal braking distance. In everyday life, these abilities of ABS are vital. ABS prevents the locking of wheels when applying full brakes. It shortens your braking distance and ensures that the car remains steerable and stable. ABS is essential for your safety. Safe braking with ABS from Bosch. Bosch, invented for life.
So this video is another interesting video to understand the safe braking that can be provided by ABS is because ABS is, what is that? It provides steering control and stability for the vehicle even at different road surface condition. That's what we witnessed, that if your right and left side wheel road surface conditions are different, you see without ABS vehicle has to spin and it cannot have instruction from the driver, whereas on the other hand the vehicle, even at that situation of different road surface condition felt by the different tires, the vehicle could stop at the shortest distance and complete total control of steering by the driver was ensured. That's what we witnessed in this video. Let's now watch another video to look at this ABS circuit and how does that sensor function, and then your ECU and master cylinder, wheel cylinder functions. What do you mean by channel? All you'll understand now, right?
This section examines the anti-lock braking system. Applying brakes too hard or on a slippery surface can cause the wheels to lock. When wheels lock, steering control is lost and, in most cases, it produces longer stopping distances. The anti-lock braking system prevents wheels locking or skidding no matter how hard brakes are applied or how slippery the road surface. Steering stays under control and stopping distances are generally reduced. It consists of a brake pedal, a master cylinder, wheel speed sensors, the electronic control unit or ECU, and the hydraulic control unit, also called a hydraulic modulator. The wheel speed sensor consists of a notched or toothed rotor that rotates with each wheel and a pickup. As the wheel turns, a small voltage pulse is induced into the pickup and sent to the electronic control unit. When the brakes are applied, the wheel's speed of rotation changes. This sends a new signal to the ECU. If the control unit detects that a wheel might lock, it sends a signal to the hydraulic control unit. In a 3-channel system, the hydraulic control unit uses 3 solenoid valves to control brake pressure and prevent them locking. The valves are in series with the brake master cylinder and the brake circuits. One operates for each of the front wheels and one controls both rear wheels. At the start of a journey, the ABS automatically checks itself. Any failure in the system lights up a warning light in the dash panel.
So these are the 3 videos I just chosen so that in short duration you would get a whole idea about this ABS. So let me just get back to my slide and continue and stop. Conclude our today's class. So let me share my screen back again. So we have looked at for understanding of this ABS functioning. For what we have to look at this graph, it's very important. So the ABS essentially makes all the time when your braking torque is applied, it would be operating in this desirable range, so that it will never take your vehicle wheels to lock, and wheel locking happens, suddenly it falls to this. So this portion never happens if we have an ABS, and this would ensure that maximum braking effort to have your vehicle stopping at the shortest distance, at the same time to also have sufficient cornering coefficient, and hence the cornering force to counter your any lateral disturbance that act on your vehicle. So that is why you have to correlate this graph with what you have witnessed in your video. And also we have looked at here the tire dynamics during that time. So as the braking torque applied because of the cylinder pressure in the wheel, and you get your braking effort developed at the wheel, and that braking effort into the radius is what is this tire wheel moment due to this, and this difference happens to be positive, then still wheel is not going for deceleration. If this difference is negative, then it is decelerating. So your application of your braking torque to ensure that the condition of deceleration, and that would be happening here. So let me just conclude what are the important parameters that we look at when you have to say a characteristic of ABS, or the parameters that are to be observed with the help of ABS system as function of time, so that you can characterize the ABS. So for that, what are those parameters? If you look at the first one is the brake pressure. And then it is your tire skid. It's not the order says that is important. So these are all the parameters simultaneously to be observed to characterize the ABS system as function of time. How does it function? When I say function of time, it is not for a duration of minutes, it's duration of seconds. Because as we say, every second the vehicle is monitored by ABS more than 25 to 30 times is what in the video that we have been here. And if you look at in millisecond duration, the action would take place. What is that action? I mean to say, the ECU sends the signal to the modulator, and the modulator would change the pressure, brake pressure in your wheel so quickly. So within a second, some 15-16 times it can increase pressure, decrease pressure, and then again increase pressure, and so on. This action can go on. So these are the parameters should be looked at as function of time. That's what I'm writing down. So brake pressure, tire skid, what's happening to that value, then vehicle speed. So your vehicle speed has to be 0 by the braking action at the shortest distance. That's the objective of your ABS. and that is with the ensuring that wheels are not locked. Then detail the circumferential speed. It's a vehicle speed, and another one is circumferential speed and circumferential acceleration. Circumferential speed is r times omega, and circumferential acceleration, that is r times omega dot. So these are the parameters of the tire as function of time during the braking maneuver should be looked at, right? So let me just take another slide and to show you this all. So what we discussed, we'll brief and then conclude our lecture. So you look at here, this tire dynamics during braking is what we just understood at the beginning of our lecture. And then we looked at what are the different elements that are there in your ABS. We understood through the slide explanation as well as that video we witnessed. And then this is what is very important that you have to understand operating characteristic of ABS. Essentially, you have to look at your braking pressure. See, you can see here. So what is that? Here is on off. So anti-lock on off signal. So when anti-lock brake is on, what is happening to the pressure is the pressure drops. But it is not dropping, it is held, and then again it is increasing, again it is decreasing, like that this action happens. During this action, what is happening, your skid value, see here, initially it is 0, that skid value goes, but it is not coming to 100% skid. That means it is in a desirable range. So maybe within the 20% itself. So you see that it is not falling. When it is falling to 100%, when you see that the vehicle speed almost reaches to 3 meters per second speed, almost it is to stop. There is no skid possibility at that time. So as the speed of your vehicle gradually decreases, as R omega value would be varying. So the omega value is fluctuating because of this pressure cyclic variation. And you see that would be accordingly. So when the pressure drops, you see there will be an increase in omega. That's why this goes to this. Now, when pressure is increases, brake pressure, then the speed decreases. So this cycle would take care, this R omega reduces, that the envelope is what is corresponding to your vehicle speed. And the pressure fluctuation you could see as function of time. In 5 seconds, it is dropping from 50 meter per second, sorry, 15 meter per second to this with the help of this ABS, right? So once this reaches the smallest threshold value of speed, then that ABS functioning would stop. So this is that operating characteristic of an anti-lock system for a heavy commercial vehicle with a pneumatic braking system is there. So here it's a pneumatic braking system. Whereas in the case of a passenger car ABS, you would have that is being by an hydraulic brake system, right? So this is what is that important aspect that you have to understand. And you see here what is happening to your R omega dot. That's what is your acceleration that are the center of the wheel, and that you see the moment your ABS act, it falls and then it goes like that, it fluctuates, and finally you see that's going to be 0, right? So this is how you have to explain your operating characteristic of ABS, and you have to choose 5 parameters. That 5 parameters are the pressure, brake pressure, vehicle speed, skid, and then circumferential acceleration, circumferential velocity, of course the vehicle velocity, as all looked at as function of time, right? So this is to be remembered. And again, the last slide, there can be various layouts of ABS. So you can have 4-channel ABS 4 sensors system, or 3-channel ABS 3 sensor system, 3-channel ABS 4 sensor system, or 2-channel 2 sensor system, and so on. So you can see here you have the requirement is steerability, stability, and braking distance. So all can be achieved by all these systems. So the objective of ABS is you should have a stable state of motion during braking, complete control on steering, and the same time to achieve, then only you can achieve the shortest braking distance. So this all can be achieved with these channels. So what do I mean by channel? A channel in this system refers to the brake system. In the brake system refers to which the control unit or modulator controls independently from the rest of the brake system. A channel that become independent. So you have 4 channel means for all 4 wheels you'll have 4 channels. So every wheel can be independently controlled. You have 3 channel, 3 sensor system. So 3 channel means the first 2 wheels, front wheels will have a channel, independently 2 channels. And rear wheel will have 1 channel where you have 1 sensor would control. So there are some strategies called low speed pickup and high speed pickup. So low speed means out of 2 wheels, whichever is the smaller speed of the wheel would be considered for the action of braking pressure reduction. And that is essentially, if you look at kind of oversteer effect, stability is the question mark, then that strategy would be select low speed strategy would be favored. Similarly, you also have select high speed strategy as well. So you have this all. So you can see here the square one is the control channel, the sensor, and then symmetrical road surface and asymmetrical road surface. So you can see here from this graph, all these channels can provide to take care of steerability in symmetrical as well as asymmetrical road surface, stability on both the type of road surface, and braking distance also in both surfaces. So these are some various layouts of ABS. So you can refer to read this again from our Wong textbook. You have nice literature and nicely explained all this. So this reference is from Theory of Ground Vehicle Wong. So with that note, I complete today's class on ABS, and that completes again longitudinal dynamics. So next week we look at closely tire dynamics and tire models, the properties of tire for your vehicle dynamics, and that would complete our course. With that note, let me stop today's class. If you have any doubts, you can ask. Otherwise, I will stop recording.